Good morning, everyone. My name is Arthur Pasqualotto, and today I'm going to present you my seminar on NJL model from quarks to stars. I am a master's student at Federal University of Santa Maria. I am a member of the research group on strong interacting matter under extreme environments. And today I want to start my talk talking about the discovery that Jocelyn Bell Burnell made in 1967. She was doing her PhD research and she found some strange signals from outer space, some pulsing radio signals that were very frequent and very fast. And it was a very exciting discovery, so exciting that they called it uh, Little Green Man, for LGM was the way they classified it. But now we know that these signals were not from outer space. Now we believe that these signals that were very frequent were made from stellar objects that we now call pulsars. It's called pulsars because they emit frequent pulses of radio signals. Pulsars were a very interesting discovery, so interesting that this band called Joy Division put this image from a radio astronomy magazine and put it on the cover of its album. But there are much more things that these objects can show us. Pulsars are believed to be very dense sphere-like objects that has the densities of nearly those of the nuclear matter. Nearly because its average density it's believed to be almost or even more of the nuclear matter. And we have no other evidence or any other reason to believe that neutron stars, are not made of nuclear matter. And actually, neutron stars are believed to be really, really small compared to stars or even planets. We the the models we studied since the discovery of neutron stars or pulsars, they are the same thing, were pointing in the direction that neutron stars would have approximately 10 kilometers in radius, around 10 kilometers in radius. So they are really, really small and cannot be observed directly. So we don't have any way to measure them directly and infer what they are made of. We have clues that from their densities, we suppose that they are made of nuclear matter, but we're not exactly which kind of nuclear matter, which proportions they exist. And since they are very heavy, dense objects, and they have masses around the masses of the sun, and they are confined in a very small region of space, we believe that the density of its insides would be of such magnitude that the quarks would appear, that the protons and neutrons that compose nuclear matter would dissolve itself and pass through this process we call deconfinement. And this process is the one that it describes in this cartoon, that the protons and neutrons are so packed together that the boundaries that defines what is a proton or a neutron becomes almost irrelevant, and the quarks become the most important degrees of freedom of the system. And this leaves us to believe that maybe the nuclear matter that compose neutron stars is actually, can be actually made of quarks and not hadrons like protons, neutrons, and other particles, but quarks, since the density is so great. And since we don't know much about the nuclear matter at such high densities, and we are still figuring out how to understand its properties, it is very convenient to use these objects, neutron stars, pulsars, to understand nuclear matter. And this is a picture of what we are supposing to be two possible ways of nuclear matter to manifestate. We still don't have, we still don't know for sure if it's inside have quarks or don't, or if they have a strict phase transition like the one on the left, with a phase transition of first order, or maybe a crossover when we have a mixture of quarks and hadrons. And this is a topic that it's still emerging from the literature, and we need to we are working this thing out yet. And this is why it's so important to study models like the NJL model. The NJL model is a effective model. One second. The NJL model is an effective model that describes quarks and their interactions, and is an effective model because it's parameterized by two parameters. One of them is called lambda, and the other is the g, and they are parameterized such as the model reproduces some experimental results. This model has a property that it describes very important effects, such as the chirosymmetry breaking that is responsible for almost all observed baryon mass in the universe, because each quark is believed to have a current mass of 5 MeV, while a proton is 1,000 MeV, and this process explains how 15 MeV will, because of the interaction of the quarks, becomes 1,000 MeV. With the Matsubara formalism...
Okay, 2 minutes.
Okay. With the Matsubara formalism, we can find the thermodynamical properties of this matter described by this field theory. And with the thermodynamic properties, we can find the macroscopic properties, thermodynamicals, and also the mass and the radius of a star, simulating a star with the TOV equations, Thoma, Oppenheimer, Volkov equations. And this is a very important method for seeing a star that might be real, and see if these stars that we simulate on computers have the same properties, or some of the observables we can observe in nature. And we can find the properties of the stellar matter that can be made of quarks. This is the abundance of fermions in the matter described by the NJL model, with 3 quarks, up, down, and strange, and electrons. The electrons are there to make sure that the model describes matter that is electrically neutral. And we can see that as the baryonic density increases, we have the appearance of strange quarks, which is a very good hypothesis that inside a neutron star, the densities may be so high that there will be strange quarks also. And with these thermodynamic properties, we can create an equation of state that is a relation between pressure and energy density. And with this equation of state, we can plug in the TOV equations, TOV, and find the mass radius diagram that shows us what are the maximum masses and radius of a possible star that might be simulated uh, if a star were made of entirely of quarks. This would be their possible maximum masses according to general relativity. So in general, we use the stars. In some sense, we use the neutron stars to guide us to a better understanding of nuclear matter. We use them as our natural laboratories. At least for now, we must be content to just look at the stars and see what they do. Thank you.
Thank you. Okay, questions, perguntas?